For more problems and videos like this for linear algebra, you can take a look at Sarai Studies, link is in the description box below. In the last video, I showed you how to go from a system of equation to a matrix. Now, let's go the opposite way. Let's see what happens when we go from a matrix back to the system of equation. So recall that each column on the left is simply just the coefficients that are next to your variables. And so by default, the variables are x's. So in this case, these coefficients are always going to be attached to an x1 and then an x2 and an x3. And if you had another column, the next 4 and so on. But these values are actually the values that are at the end after the equal sign. And each row is just its own equation. So we will have 3 equations. So have 1 x1 plus 0 x2 plus 0 x3 equal to 1. Then I have 0 x1 plus 1 x2 plus 0 x3 equal to 2. And then for my last equation, my last row, I have 0 x1 plus 0 x2 plus 1 x3 equal to 3. And now we went from a matrix back to its system of equations. Now let's do the same for this one. Again, these are just our coefficients, and these are our end values. These coefficients here are going to be multiplied by x1 and then x2 and then x. Remember, each row is an equation. So I'm just going to do 1, -1, 0, 0, these numbers right here, and just do x1, x2, x3, and then equal. Then for my second equation, I'm just going to write down the numbers 0, 0, 1, -2. Then just put down the variables. So x1, x2, x3, and they're all pluses, and then equals. And then for my last equation, the last row is 0, 0, 0, 0, equal. And then x1, x2, x3, when they don't have a sign, it's positive, and that's equal to 0. Now, let's look closely at these. There are a lot of zeros. So let's start with this one. What happens if we remove all of the zeros from here? We're left with this, which is interesting because if we move these things over to the side and then ones are insignificant so we can remove the ones as well, what are we left with? We're left with what each variable is equal to. x1 is equal to 1, x2 is equal to 2, and x3 is equal to 3. Now let's see what happens when we remove the zeros here. In this case, we're left with this. We can move these over. Ones are insignificant, and then here we have essentially 0 is equal to 0. So this is telling you that x1 minus x2 is equal to 0. This is telling you that x3 is equal to -2, and it's telling you 0 is equal to 0. Now this is very interesting. When we translated this matrix back into its system of equations and removed all the jargon, we got unique solutions to each of our variables. Unique because every variable has its own value. Then when we translated this matrix back into its system of equations, we got solutions, but they're not unique. How do I know they're not unique? Because as soon as you see 0 is equal to 0, that means that there are many solutions. Remember, what are we talking about when we say solutions? These just represent lines. And so when we see solutions, these are where the lines intersect. So in this case, we have unique solutions, but in this case, we have many solutions. And we will get to this in another video, but the thing that we do to properly write our many solutions is we write it in terms of a free variable. A free variable is a variable that's free to be anything, so I'm not going to show you how to actually find it in this video because that's for another day, but let's just say the free variable is x2, so we write everything in terms of x2. So in other words, this here goes to the other side. It's just going to become a positive. This we can remove because it's irrelevant, and then we specify x2 can be x2, whatever it is, anything. So now x1 is x2, it's in terms of x2. x3 is -2, and x2 can be anything. So this is the way that we write our many solutions in terms of the free variable, which we will talk about in another video. But the point of this video is to show you that if these types of matrices, when I write them back into their system of equations and simplify, they give me the solutions to the system. Maybe I want to get all of my matrices to look like this because then I can find the solutions to its corresponding systems of equations. So what's beautiful about linear algebra is that getting matrices in this form where you can find its equations once you rewrite them back into their system of equations is called reduce row echelon form. So our goal in this lesson is to get every matrix in reduced row echelon form so that we can rewrite it back into a system of equations and then find either unique solutions or many solutions, or sometimes it will have no solution. And the only time it has no solution is when you have something like 0, 0, 0, but then this is a 1. 0 is equal to 1 is not true, so therefore that would be a no solution. Meaning that these three lines, right, every row represents a line, an equation of a line, don't intersect. That's what it means for a system to not have a solution. That is the goal. You want to take your matrix A of B over here, your augmented matrix, and put it in reduced row echelon form. But here's the fact. To get to reduced row echelon form, you actually have to get to row echelon form in the first place. Because reduced row echelon form is just row echelon form, but reduced a little bit more. So other than the fact that we need row echelon form to get to reduced row echelon form, why would we want row echelon form? Number one, it saves us time, because when we get to this form, we oftentimes see that there is no solution. When do we know there's not a solution? When we have something like this, but then this is a 1. So this is 0 is equal to 1, and that's not true, so therefore we can see that there's no solution, so there's no point in getting to this form to use it to rewrite our matrix like something like this back to a system of equations so we can get solutions, because we already found out that there's no solutions. So number one, it saves us time. And then number two, in future lessons, we will be reducing matrices not for the purposes of solving systems of linear equations, but for the purposes of answering other questions, and we don't need to get to this form to answer those questions. We can just get to this form and answer those questions. So it's useful knowing just this. So the summary of this entire lesson is that we're going to be given a system of equations. We can rewrite it as a matrix A of B, and then we can find the row echelon form of our matrix A of B. And then if we see there's no solution, like we literally see sum 0 is equal to 1, and we know that's not true, then we can just stop there and now continue on to reduce row echelon form to get our solutions, because hey, we already know there's no solution. But if we don't see signs of no solutions, then we can continue on reduce row echelon form of the same matrix, just to be clear, so we can rewrite that back into a system of equation that's easier to solve, easier to extract the solutions. So in the next video, I'll show you what it means for matrices to be in these forms, what they look like, and in the video after that, I'll show you how to actually get matrices in this form. And then the video after that, I'll show you how to actually answer questions, going through the entire process given a system, and then getting the solutions by rewriting the matrix into these forms. So I'll see you in the next video.